Hello students, welcome back. Let us resume our discussion on hypothesis testing. The structure of hypotheses are like these, or like those. They're equivalent. If you take the difference between two proportions, you're going to get these, and then you can compare those with 0. And this is going to be more convenient for graphics and also actually solving a problem. Now, the second form, comparing two proportions, this is going to be more convenient in getting the standard error. First, reconcile this pi1 and pi2 by this form, adding up the numerator and adding up the denominator, and then getting a new fraction. And then using that new fraction, you get this formula for SE. And we use all those for setting up appropriate hypotheses and sample statistics for this problem. Remember, a salesperson for a new manufacturer of cell phones claim not only that they cost the retailer less, but also the percentage of defective cell phones found among these products will be no higher than the percentage of the defective found in competitors' line. Well, it used the term no higher than, kind of confusing, but basically the extreme case is about the same. Now, to test this, we did some sample study and we got these, and it looks like there's significant difference. 15 defective out of total 150, so 10% defective. 6 defective out of 150, so that's 4% defective. To tell the truth, I think both are outrageously high, but I don't know, this is just classroom example problem, not actual cell phone manufacturers. I mean, 15 defective out of 150. Any company like this, it must have gone broke by now. Anyway, let's review the setup of the problem, and then now let us complete the solution. Okay, first, the critical value method. Here's the setup. The proportions are like this. 15 out of 150, that's 10%. 6 out of 150, that's 4%. And the difference, you have 6% of difference. That's the observed difference. Okay? As far as the hypotheses are concerned, you're going to compare those with 0. So 0 versus 6% point difference. All right, is it a significant difference or just a little bit? It's hard to tell. All right. Now, how do we reconcile this 10% and 4%? We do this, add up the numerator and add up the denominators and get a new proportion. Why am I doing this? Under the null hypothesis, pi1 and pi2 are about the same, which means salesperson's sample and competitor samples are essentially the same, no difference. So there's no difference between these two samples, therefore just putting all together into one big sample, and we end up with 21 defective out of total 300, and thus 7% defectiveness. And that's the proportion we use to calculate the standard error. And if you do that, we get this number, and that's the number we're going to put into the denominator. And also, here's the setup. Null hypothesis is always no difference. So, okay, no difference there, or the difference is about the same as 0. Alternative hypothesis, the salesperson's company has higher defective rate. Okay, all right. Now, let's go ahead and solve it, but let me show you a picture first. So it's kind of like this, centered at 0, the null, and we are looking for the critical value. And, well, according to this, the critical value turns out to be about 4.8% something, so 6% difference is too big. So it looks like it's going over to alternative, but we can come back and discuss that. The key point is to find out this critical value. Critical value where this red area outside is 5%, consequently this blue part is 95%. How do I do that? Well, the typical n minus center over SC. Do that, and then you compare that with appropriate z-score for here. N minus center over SC. Center is 0. So what do you have? X over the standard error, which we calculated over there, is the z-score associated to 95%, 1.645. Here I use a little bit better figure using Mathematica, so 1.64485. And then solving for x, something we had been doing all the time. So what do we have? We have 0.048 something. Let's go back to the picture. This threshold or critical value is about 0.04846, definitely less than 0.06%. So the 6% point difference is far away from null, too far away from the null, so that you have to reject the null and take the alternative hypothesis. In other words, the salesperson's company has higher defective rate. Now let's do probability value method. Same setup. P1 and P2, 15 out of 150, 6 out of 150, and the difference between the two is 0.06. And reconcile those two. Add up the numerators and add up the denominators and get a new proportion. Basically, getting one big sample out of those two samples put together and jumbled up, and use this proportion to calculate the standard error. Once you do that, you get the standard error. That'll go to the denominator in the z computation. As for the hypothesis, pretty simple. Null, no difference, so difference is 0. Alternative, greater than 0. Alright. And the picture is like this. Null is 0, and 6% point difference was the observed difference. Alright, you get this red area, and that probability. And what is that? This is a conditional probability that under the assumption null is right, you end up with the sample result like this, or possibly worse. It turns out that by the symmetry and all, that probability is the same as the probability that null is right, given that we ended up with a sample study result like this. So the probability that null is right is not very big. It has only 2%, less than 5%. So null is likely to be wrong. So you go with the alternative hypothesis. And for the computation of that probability value, pretty straightforward. N minus center over SC, and you get that, and look up that from the Z table, and you're going to get the probability value. Or you can use statistical calculator like this, which will give you a little bit better approximated figure than normal table. In any case, you can clearly see that the p-value, the probability value, is less than the significance level. So the probability that null is right is too small, so null must be wrong. We go with the alternative hypothesis. Finally, confidence interval method. That's not going to work for proportion. Why? Because we have two different SE. You see this SE versus this SE. For confidence interval, we use this SE formula. For hypothesis testing, we use this SE formula. They're different. So just applying confidence interval to the hypothesis testing is not a good idea in two-sample inference for proportions. Generally, it's a bad idea for proportions, actually. For means, most of the time it works, but for proportions, it doesn't. And here's an open-ended question. What if you test for 1%, significance level of 1%. Previously we did for 5%, so the result was alternative. We go with alternative, which means salesperson's company indeed has higher defective rates, so you should not purchase that. And as for 1%, well, you can do that. Let's see, do we have a solution? Yeah, it's left to the students. I'll just show you some pictures. So change it to 1%, all right, 1%. If I do that for 1%, then looks like null hypothesis would win. So the critical value goes to 0.068 something, while the observed difference is 6% point. So according to at a significance level of 1%, we get, bigger blue region, so higher chance of going into null hypothesis, and indeed that's what happened here. If you use the probability value approach, we get this. So 0.06, and then calculate this probability. And this probability, well, the same probability computation as a matter of fact, and then it is 0.02 something, so 2% is greater than 1%. So if you use the threshold, the significant level as 1%, then the probability that null is right is larger than your cutoff line. So it's likely that null is right. So we go with the null hypothesis. So we get different conclusion by changing the alpha values. Originally we did for alpha 0.05 and repeated for 0.01. The detail for 0.01 case or any other alpha value is left to the students. That completes section 2.